Hey everyone, and welcome back to the channel. Today, we're diving into one of the weirdest, most mind-bending concepts in modern physics, the Unruh effect. It's a prediction that sounds like straight-up science fiction, but it's rooted in some of the most fundamental theories we have about the universe. So, what is the Unruh effect? In a nutshell, it says that if you accelerate through empty space really accelerate, you'll start to see a warm glow, a bath of particles, as if you were surrounded by a heat source. But here's the kicker. An observer who isn't accelerating, floating right next to you, would see nothing. Just empty space. Sounds crazy, right? How can one person experience heat and particles, while another, in the same region of space, sees only a vacuum? To understand this, we need to talk about a few key concepts: quantum fields, vacuum energy, and what it even means to accelerate. First, quantum field theory. Forget the idea of particles as tiny billiard balls. Instead, imagine the universe is filled with underlying fields, one for each type of particle. There's an electron field, a photon field, a quark field, and so on. These fields are constantly fluctuating, even in what we think of as empty space. These fluctuations give rise to what we call vacuum energy. Even in a perfect vacuum, with no real particles around, there's still a seething sea of virtual particles constantly popping in and out of existence. They're not real in the sense that they can't be directly measured by a stationary observer, but they're crucial to how the universe works. Now, for an observer at rest, or moving at a constant velocity, what we call an inertial observer, these virtual particles remain just that, virtual. They don't interact in a way that produces any observable effects. The vacuum looks empty. But things get very different when you accelerate. Acceleration isn't just about changing speed, it's about changing your frame of reference relative to the quantum fields. From the perspective of an accelerating observer, the vacuum energy, those virtual particles, gets distorted. This distortion is the heart of the Unruh effect. The accelerating observer's motion through the quantum fields essentially promotes some of those virtual particles into real particles. They start interacting with the observer, creating a thermal bath, the glow of radiation. This is called Unruh radiation. The temperature of this Unruh radiation is directly proportional to the acceleration. The faster you accelerate, the hotter the glow. And this temperature isn't just a mathematical abstraction. It's a real temperature, in the sense that the accelerating observer would measure it with a thermometer. Think of it like this. Acceleration creates a kind of event horizon for the observer, similar to the event horizon of a black hole. Information from certain regions of spacetime becomes inaccessible, and this information loss manifests as thermal radiation. This connection to black hole physics is one of the reasons the Unruh effect is so fascinating to physicists. Now, you might be asking, if this is real, why haven't we seen it? The problem is the acceleration required is enormous. To see an Unruh temperature of just 1 degree Kelvin, you'd need to accelerate at roughly 10 to the power of 20 meters per second squared. That's, well, let's just say it's beyond our current technological capabilities. While we can't directly observe the Unruh effect with current technology, it has profound implications for our understanding of gravity, quantum mechanics, and the very nature of spacetime. It suggests a deep connection between acceleration, temperature, and the quantum vacuum. The Unruh effect is a testament to the strangeness and beauty of the quantum world. It reminds us that even the most seemingly empty spaces are teeming with activity, and that our perception of reality is deeply intertwined with our state of motion. It's a concept that continues to challenge and inspire physicists, pushing the boundaries of our knowledge about the universe. Thanks for joining me on this exploration of the Unruh effect. If your mind is as blown as mine, give this video a like, subscribe for more mind-bending physics, and let me know in the comments what other bizarre concepts you'd like me to tackle. Until next time, keep accelerating your curiosity.